Okay, picture this. You're holding a grain of sand in your hand, and somehow you know all its size, position, and shape information perfectly. Now shrink that grain of sand down to a trillionth its size, a fundamental particle. Would you still know its position and shape? Or would the laws of the universe start to break down? That's where non-commutative geometry jumps in, flipping the script. Imagine if space-time itself wasn't a smooth canvas, but more of a fuzzy grid stitched together by quantum uncertainty. I promise, it's a concept more mind-bending than sci-fi. Stay with me, because today we're taking on a wild thought experiment that redefines what our universe is made of. Okay? Ready? Let's go. Oh, hi there. Welcome, or welcome back. I'm Olympia, and let me take a moment to say, if you're here exploring these intricate ideas with me, I think you're amazing. And thank you for being part of this small but curious, hyper-focused community. It's growing because of you. So thanks for sticking around on this deep dive into the weirder side of reality. Go grab a coffee, or tea, because today's topic is going to make you see space-time as, well, completely different. Okay, let's rewind for a sec and start with regular geometry. In your everyday experience, the geometry of space is straightforward, right? You've got lines, surfaces, and points, and they all obey neat rules. Take a flat table. You can place a ruler down in any direction and measure distances consistently. Simple enough? Now, classical physics treats spacetime, a blend of space and time, as a four-dimensional, smooth structure, like a vast fabric. You can measure distances between 2 points in spacetime cleanly. That's how Einstein's theory of general relativity treats it. But what happens when we zoom in? Classical math collapses as spacetime gets super tiny. It doesn't play by the same rules. At quantum scales, smoothness dissolves into chaos. A fuzziness emerges as the precision of one measurement affects another. Take Heisenberg's uncertainty principle. It tells you that you can't precisely determine a particle's position and momentum simultaneously. Now extend that uncertainty not just to particles, but to space-time itself. Space-time becomes non-commutative. What in the world does non-commutative mean? Okay, let's break it down. Commutativity is something you've known since grade school. 3 times 2 equals 6. And hey, 2 times 3 is still 6. Order doesn't matter, right? But math gets fancy when we deal with matrices. Think grids of numbers instead of single digits. With matrices, the order does matter. Switch them around and the result changes. That's non-commutativity. Now, physicists started asking, what if space-time itself had its own non-commutative structure, built into the fabric? What if the universe wasn't this precisely definable grid, but an unpredictable, jittery network? And from this, the concept of non-commutative geometry was born. But why, you ask? Why even entertain such a bizarre idea? Here's the thing. The smoothness we take for granted has never been observed at the Planck scale. That's 10 to the negative 35 meters, by the way, an unimaginably tiny scale. That's the size where quantum mechanics and gravity smash together into contradictions in the math. Non-commutative geometry is one way to resolve this clash. Instead of imagining points of space-time as infinitely definable zeros, it replaces them with fuzzy patches, where uncertainty reigns supreme. Now let's bring this closer to Earth, or closer to reality anyway. If space-time is not smooth, but grainy, what evidence would we have? Amazingly, this isn't all just theoretical guesswork. Let me blow your mind for a second. Certain limits on the smoothness of space-time have already been probed using advanced detectors, like LIGO, the setup you've probably heard about for detecting gravitational waves. Although LIGO hasn't yet conclusively found evidence of space-time fuzziness, it's sensitive enough to hint that non-commutative geometry might be more than science fiction. Crazy, right? But here's where the rabbit hole deepens. Non-commutative geometry isn't just an odd reinterpretation of space-time. It's also a mathematical language for handling the strange quirks of quantum mechanics, when particles move like waves, or waves act like particles. It turns out, you can use non-commutative geometry to rewrite the equations of quantum field theory. That's the quantum machinery used to describe particles at fundamental scales. With this rewritten framework, we gain new tools to bridge quantum mechanics and Einstein's general relativity, a feat physicists have chased for decades. Suddenly, the fuzziness seems less ridiculous, right? Let's tackle some nuts and bolts. In non-commutative spacetime, positions and momentum, operate mathematically not as classic numbers anymore, but as matrices that don't play nice with each other. That non-niceness, it injects uncertainty directly into spacetime. At every point of reality's fabric, measurements bleed into one another, refusing to be pinned down absolute values. Sounds messy, but that messiness helps explain deep features of black holes in quantum fields where traditional math simply breaks. Speaking of black holes, oh yes, did you know they've become poster children for this idea? Because black holes are these ultra-intense regions where quantum effects absolutely cannot be ignored. A black hole might look like an enormous cosmic maw from far away, but zooming in past the horizon, where space-time stretches to insane limits, the fuzziness of non-commutative geometry plays a crucial role in the equations predicting what's inside. Could the edge of a black hole, the so-called event horizon, actually encode information in this fuzzy matrix structure? Some physicists think, yes. Okay, here's another angle to think about. A lot of people wonder, if this theory is right, why haven't we seen atoms or photons, shaking around with this fuzziness? Shouldn't it be obvious? Well, no. The graininess predicted by non-commutative spacetime only shows itself when you crush down to incredibly tiny distances, trillions of factors smaller than anything occurring in day-to-day phenomena, or even inside atoms. Talk about scale, huh? This means we may need particle accelerators much more powerful than anything today to directly test these predictions. But, and here's a huge but, even without directly observing non-commutative spacetime, the math holds staggering potential. Let me give you a quick metaphor. Think of classical geometry as a clear view out your car windshield. Non-commutative geometry, it's like switching to night vision in a fog. Different tools, different picture, and you may just see what's invisible otherwise. This framework might even give us clues about big mysteries like why the universe expands the way it does. Scientists suspect the fuzziness at smaller scales could have cascading effects shaping larger cosmic structures over billions of years. And here's your wow moment for today. Brace yourself. Some interpretations of non-commutative geometry suggest spacetime might not even exist continuously. What? Yeah. It raises ideas that spacetime emerges from something deeper, like a quantum dynamic or relational network. This breakthrough idea is shaking foundational physics today. Because if spacetime itself emerges from something more fundamental, then everything we call reality shifts one rung beneath where we think it starts. Boom. So you might ask, what now? Are experiments being developed to nail down the truth of non-commutative spacetime? Absolutely. Next-gen observatories, from interferometers to deep space probes, aim to test how wave interference patterns bend if spacetime subtly deviates from smoothness. Yeah, we've got a long way to go, but these are the seeds of an absolute revolution in understanding existence. After all, doesn't every massive breakthrough start with a totally wild idea? All right, to wrap this mind-bender of a topic, non-commutative geometry challenges everything we thought spacetime was. A continuous, predictable canvas, and reimagines it as grainy, fuzzy, and fundamentally quantum. It bridges gaps between quantum mechanics and relativity. It could explain black hole mysteries, and it might redefine physics as we know it. So what do you think about this strange, wacky picture of the universe? Let me know below. I love reading your thoughts. Be sure to give this video a like, subscribe to Hyperfocus if you haven't yet, and keep sharing these insane ideas far and wide. Stay hyper-focused, and remember, the universe might be fuzzy, but thinking deeply will always sharpen your understanding. Bye for now.